Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we're joined by Vladimir Bychkovsky, engineering manager at Facebook, to discuss Spiral, a system they've developed for self-tuning high-performance infrastructure services at scale using real-time machine learning. In our conversation, we explore the ins and outs of Spiral, including how the system works, how it was developed, and how infrastructure teams at Facebook can use it to replace hand-tuned parameters set using heuristics with services that automatically optimize themselves in minutes rather than weeks. We also discuss the challenges of implementing these kinds of systems, how to overcome user skepticism, and how to achieve an appropriate level of explainability. And now, on to the show. All right, everyone, I am on the line with Vlad Bychkovsky. Vlad is an engineering manager with Facebook based out of the Boston office. Vlad, welcome to This Week in Machine Learning and AI.
Thank you. Thank you very much. It's very exciting to be here.
So today we're going to be talking about a project that you have worked on called Spiral. But before we do that, I'd like to explore a little bit of your background. You did your graduate work on image enhancement. Tell us a little bit about that.
That's correct. Before that, I did a little bit of systems work as well. So I worked in wireless networking and then transitioned into computational photography, primarily because I really enjoyed photography and I wanted to learn more about it. So for my thesis, I worked on automatic image enhancement, which is the magic button that people have on their phones, or actually the algorithm I developed is now in Adobe Photoshop. If you dig deep through the menus, you could automatically set curves, and that's the algorithm that I built during my thesis. And then after I finished my PhD, I joined Facebook.
Nice. And what group are you in Facebook?
The group is called Machine Learning Experience. And it's a group. The goal of our group is to basically deliver the benefits of machine learning for everybody. Generally, machine learning is kind of thought of as kind of this elite field where only people with incredibly strong backgrounds can contribute or even use. Whereas what we're trying to do is kind of democratize machine learning so that every engineer at Facebook can benefit from it.
Okay, and the specific project that you're working on is one called Spiral that your group disclosed recently. Tell us a little bit about that project.
Sure. Yeah, this is actually, I think it's a very exciting project. I'm glad to be part of it. I think I thought for a while about how to describe what we do to people who are not necessarily deep in computer science. And I think the best analogy is the following. So if you think about, for example, like coffee drinking habits. So we all want to sleep at night. At the same time, people do enjoy their coffee. And if you have to make a decision, do I drink coffee at 3 p.m. or not? Right? You can do a bunch of experiments where you drink coffee at 3 and then see if you can fall asleep at night, right? And based on the result, you kind of adjust what was the right call. Like, for example, I drink my coffee, then I can't fall asleep. Okay, I record the outcome. And then the same thing next day. Maybe I don't drink coffee after 3 p.m. and I fall asleep fine, right? And sort of you kind of build up the data set and you kind of define a policy for yourself. You learn a policy, which is, I shouldn't be drinking coffee after 3, right? So the same kind of thing can be done for machines, where you can literally, in this environment where everything around you is changing all the time, you could kind of see the results of your actions, and you could see in retrospect whether or not the actions the machine has taken were good or bad, and inform future decisions. Does that make sense?
So that is a really, really good explanation and example. And I think you may have just derailed the interview, because the thing you just described, I really think it needs to exist. Like, I've wanted the quantified self movement. I don't know if people even talk about this anymore, quantified self, but I've wanted this thing that just like tracks you can, set up some metrics and track data points, and then it applies machine learning to figure out the correlation between your actions and, these other experiences you have, whether it's, health or happiness or, what have you. It automatically uses this data that you collect to make predictions, as opposed to, what quantified self really ever amounted to is providing like pretty pictures
Yeah, that's right.
of the past, like the rear view mirror, as opposed to the,
Yes.
the dashboard.
And I can tell you more about why it's so important for Facebook, or generally, I think any company of that scale or any company that wants to scale, if you're interested.
It sounds like you're not going to let me derail the interview by talking about applying this to quantify
No,
self,
no.
which is good, But it sounds like a set of problems that you can maybe loosely or roughly refer to as, I don't think they're as low level as infrastructure management, but you're kind of using them to manage the way you configure, if not low level infrastructure, like high level, software and kind of the deployment architecture of. Actually, I don't think deployment architecture is the right term either, but the configuration of software components that are driving various Facebook applications.
Yeah, that's right. So another way, like the way I call it internally, sort of more formally, it's automatic adaptive policy, right? So it's automatic policy learning, where instead of usually people define policies like coffee drinking policy or cash admission policy in terms of some sort of heuristic, right? They sort of look at like, oh, well, let's look at arrival times, let's look at something else, and let's have a bunch of if-else statements where we define the behavior. And that's generally works pretty well. There's nothing wrong with that approach in normal circumstances. I think the biggest challenge for this comes up when you actually start going sort of at a much higher speed. Specifically, you think about Facebook, and this was published on our engineering blog a while back. Facebook is releasing a new version of web source code every hour. So literally, the version of Facebook you see is different from an hour to hour. So the code that runs it is changing.
Mm-hmm.
And any system that depends on the code and makes assumptions about this code can potentially be outdated within hours. So if you think about sort of www or the web of Facebook being a dependency, it's something you kind of think it should behave a certain way if your service depends on it. And then every hour it's actually changing. So whatever assumptions you made about how it behaves may be completely invalid, and not just invalid at some sort of slow rate. It literally every hour it could be different. And so in that environment, it's very, very hard to sort of keep pace and update your code, update your logic of your service to stay optimal. So it's literally, this is not like some mechanism that we just implemented because it's cool and we wanted to do it. It's literally a necessity to be able to run something at this scale and run it efficiently. So I'll give you an example of a cache, for example. So if you have cache that's caching images, it could be movies, could be anything else. And let's say that in the past, people have uploaded mostly PNG files, and we cache them. And for PNG files, we may choose a certain limit. If the file is a PNG file and is less than a certain size, let's cache it. If it's too big, let's not cache it, vice versa, etc. Like, you could sort of define a policy by hand with if statements. And then a little bit later, users are not uploading PNGs anymore. They're mostly uploading JPEGs, right? The policy you have written is completely useless because you're not caching any JPEG files, and your system performs very poorly, right? So somebody has to go in and manually recode this. Somebody has to notice that metrics are out of whack and has to recode it by hand, which is not sustainable, right? Given how fast things are changing. And so what we do instead, something like Spiral can actually learn the optimal policy on the fly as the changes are occurring, as the changes in load are happening.
And so you're talking about learning the policy on the fly, and that makes me think about techniques like active learning. Is that formally something that you've employed here, or is it an adjacent area?
It's related. I would say active learning is something we can do. It's something that we do in some other contexts. Currently, we don't do active learning inside Spiral. That's not really necessary. So active learning is more about choosing examples to train on, right? So to be more specific, imagine if you're doing medical experiments, right? And you're doing sort of experiments using new drugs or something like that. If you and you're trying to figure out which combination of drugs works better, right? And each experiment costs you a lot of money to run. Like it's literally not free, right? In this case, you can't just say, okay, let me take a bunch of random combinations and see which one works out. What you want to do is you want to take all previous experiments into account and figure out which combination to try next that gives you the most information, right? That kind of gains you the most information. In our case, that's not the setup we have, but this applies in some other situations, such as automatic configuration of services. So this is kind of looking a little bit forward, but something we're looking into sort of in the same vein of self-maintaining services or self-optimizing services is self-tuning fleets. So if you think about a number of parameters that a given service has, it's actually very large and it's actually often not clear how to set them, especially if the environment is changing. So it could be numbers such as number of threads or sizes of queues, etc. Right? And what is the optimal setting today may be different from the optimal setting tomorrow. And so what you want to do is you could use some of the machines in your fleet for experimentation, figure out which of them results in a better QPS, like the number of requests per second, right? And pick those parameters. And ideally, you do this continuously. And so this is exactly where active learning is very useful, because you don't want to use lots of machines, sort of just waste resources. You want to focus on the next combination of parameters that's more likely to be better than the current one. Does that make sense?
No, that does make sense. And there's definitely this kind of sense or definition of active learning that's focused on trying to identify the training data, for example, that increase information gain so that you can reduce your overall costs of training. But there's also this sense, or I could be just, I could be confusing ideas, but I also get this sense of active learning, or think of it in the context of like incremental learning, meaning you get a piece of, you've got a trained model, and then you get a piece of data, labeled data incrementally without going through an entire retraining. You're using that to enhance your model. Is there a better name for that than active learning?
Yeah, the better name for that is online learning.
Okay.
So it's kind of like streaming. So if you think of streaming databases, so online learning is the form of kind of learning that's streaming, right? And that's actually exactly what we use for our system. And the main benefit of it in practice is feedback loops. So it's something actually machine learning researchers rarely think about. But as an engineer trying to, let's say, enable adaptive policy in my service, I don't really want to spend time setting up a pipeline and finding out tomorrow that I made some sort of mistake, right? Because it takes a while to do the training and then to ship the data and to get me back the model. It's a very difficult feedback loop. So if I'm debugging something, it's just not really acceptable, right? So if I'm training a huge neural network somewhere on the back end, it's just difficult. Literally, imagine if you were trying to write a program and every time you compile, you have to wait a day, right? Realistically, we would not get anywhere. So,
right.
So the online models actually really help in this case, because with our system, one of the modes of operation is that when it's fully embedded and online, which means you literally plug it in, there's effectively two call sides, and you plug in the data and you literally run your service. And as soon as your service starts running and providing feedback, you can start seeing the results. You can start seeing the results improve, and you could see, oh, maybe I'm missing an important feature. Maybe I'm misclassifying something. Immediately change it, run it again, and you're good to go. Again, you can see the results immediately. So that is exactly where online learning is very, very beneficial in practice. Right. So in theory, people often talk about how, maybe you can't do quite as well online as you can do offline. Well, when you have all the data, something we're doing is we're kind of combining the best of both worlds. Online learning is used to enable really, really tight feedback loops, because to me, this is probably the most important thing in engineering. If you're building something, you want to know how well it's doing, right? You want to know how well it's doing right now, not not 3 days from now, because you may lose context, you'll forget what you were doing, what you were trying to do, et cetera, et cetera. And this is something our system enables. When you're in the steady state, when you already figured out your features, you debugged your system, everything is good. Now it's more about, okay, can I get a better, higher accuracy for my predictions? Then you can switch to offline learning mode and sort of, because the system was already debugged. And then you just improve your accuracy by using potentially larger model and more models and more complicated models. Does that make sense?
It occurs to me that I tend to think of that transition as being the opposite direction, meaning that you start with an offline trained model and you use online learning to keep that model updated. But what you've done is you've kind of flipped that and you're using offline, or rather online learning, as a way to bootstrap very quickly and without requiring the model creators to, understand the environment as well, collect the data, do all the feature engineering that, they can do when they have that data and understand the environment. And then, use the information from the online learning models that you've created to, create incrementally better models by doing, batch training.
Yeah, no, that's exactly right. Yeah. And so the challenge is always, so unlike traditional data sets, when you actually know what your features are or have complete data set, when we're talking about system generalists trying to optimize the system using machine learning, they don't necessarily know the features ahead of time, right? There's no data set. They're still trying to figure out, okay, is file size important for my caching policy? Maybe, maybe not. Is the name of the data center from which this data comes in from, is that important? Should I add that? Should I not add that? And in some respect, there's no data set before you start collecting it, right? It's sort of as soon as you say, oh, I should probably add file size, I should probably add something, then you create a data set. But it's really up to the engineer to plug it in, right? It doesn't come prepackaged as a set of benchmark of like, okay, here's a bunch of images and here's a bunch of labels. Here's a cat and here's a dog, right? It's sort of part of the problem is that people are trying to understand their problem and trying to define it as they're solving it, right? And this is actually one of the kind of probably biggest challenges for us, and sort of something I find really, really exciting about this field is that we get to change how people think, literally. So when traditional engineers come to us with problems, they always sort of think in terms of those fixed policies or sort of heuristics and picking some sort of thresholds for things. And when we start working with them, their mind opens up and they realize that they can apply this whole slew of statistical methods to a problem which they considered very, very rigid. And so to me, that's just like one of those, seeing those aha moments is really exciting. And oftentimes what happens next is that people realize that there's a whole bunch of new features that they could enable by switching to using a statistical approach from sort of a rigid heuristic. So there's kind of a bunch of really cool side benefits that come from learning more about how to apply systems like that.
And so, practically speaking, if I'm developing a system, say a caching system, one of the first things I might do in my system is pull a bunch of configuration information from, environment variables or configuration files or what have you. Instead, using Spiral, I'm calling an API to give me the kind of current best version of those configuration parameters. Is that correct?
Yeah, almost. So in some respect, there's two ways to think about it. So if you think of a complete clean slate where your system boots up for the first time and Spiral never has seen any data, so something that, and then you ask Spiral for predictions for a given item that comes in. Like, do I cache this? Do I not cache this? The Spiral will just return the default value that you assigned because it has no information at this point. But as soon as your system starts providing feedback, as soon as you say, oh, I should have cached this item, oh, I should not have cached this item, as soon as you start putting this information in, the next prediction that you ask for will be better. And so all you need to do is just pull the information at the time when you, at the time when you know what decision should have been made, right? So when you're sort of for cache, it may be at eviction time when you're evicting an item and nobody has ever requested that item. You could say, well, I probably shouldn't have cached this, right? If it's like it wasn't necessary, like nobody asked for it. And vice versa, if you see an item that's been hit many, many times, you're like, okay, definitely next time I see something like this, I should cache it.
Yeah, I think you just pointed out an important distinction, and that is Spiral is not predicting for me the underlying configuration parameters that I might use to make a decision. It's predicting the decision, meaning it's not predicting. I'm not using it to tell me, what queue length or, how much JVM memory I might need or something like that. It's operating at a higher level, and it is managing all those parameters under the covers. Is that correct?
Indirectly, yes. It's managing the parameters of your policy, right? So, for example, if you had a threshold before of, I should not cache images that are larger than 100 kilobytes, right? So you kind of had this 100 kilobyte parameter. And then you're like, well, maybe I should change it to 70 or 120, right? So, and then you look at the quality of decisions, say, oh yeah, 120 is way better. It looks like I get a better cache hit rate or something, right? So that's taken away. So if you were trying to configure a policy, you no longer have to do that. You just provide examples of correct decisions, and Spiral learns the rest of it. The tuning of parameters of a service is sort of a different project we're doing, which is kind of looking forward at the things we're interested in. So we could tune the number of threads, but the setup is a little bit different than Spiral. So in that setup, what you would do is you would provide statistics of how well the service is operating as a whole with a set of parameters. And we would look at those statistics and let's say the number of requests per second that the service is providing with a given configuration. And we would compare it to other experiments we have run. And then using active learning, we would pick the next experiment. Okay, sounds like the queue size of 100 looks better than 110. Let's try 90. Right, and that all happens behind the covers, so under the covers, and the engineer never has to see it. In the end, what they get is, looks like currently you get the highest number of requests per second if you use the queue length of 35 and the number of threads 15. Right now, you just set that to your service, and all of a sudden your utilization drops. You're consuming much less energy, and you're serving many more requests.
Got it. But that's a separate future project.
That's correct. Yes.
So then with Spiral, I'm imagining that, and you alluded to this, that engineers might have previously envisioned very simple policies for different aspects of their systems. For example, cache based on file size or cache based on file type. And now, by being able to specify these policies more declaratively, there's also a tendency to make the policies richer. Is that the case?
Yes, it's sort of a very easy way. It's formalizing the problem, right? So you use exactly the right language. So you kind of doing more declarative programming than imperative programming. You declare what it is that you want. One interesting thing that happens when we start working with different engineering teams that want to try sort of using automatic policies is that they realize that their problem is not well defined, right? They say, we really want to just optimize this metric, or this is that's what we want. And then when we try to formalize the problem, because they have to code up that declarative solution to, okay, this is the right answer, this is what the right answer looks like, they realize, that conflicts with this other objective. No, that's not what we want to do. And so this change in mindset that happens, it's also beneficial in the sense that people figure out problems that they've always had, but previously just had some sort of hard-coded solution that made some sort of implicit trade-off, right? That sort of the trade-off was hidden and fixed, and they just lived with it. And switching to this higher level programming model effectively forces them to be more explicit about the trade-offs they're making, understand the trade-offs they're making in the system. So again, I think this is one of the super exciting aspects of working in this field.
Can you walk through an example that illustrates that, both the specific changes that they need to make to implement these policies and to integrate with Spiral, but also where these types of trade-offs have come into play?
So, I mean, it's difficult to do sort of an abstract, sort of an example that would be easy to discuss on sort of on a radio without a blackboard. But if you think about, again, something like cache admission policy, right? You sort of want, as soon as you are, previously you could just say, oh, well, I think we should cache this type of files, and if they're not bigger than this, right? And just roll with it. And then you look at some metric and see, oh, well, the cache hit rate looks good. All right, that's fine. Let's keep it as is, right? So you don't know what the opportunity cost is, right? So maybe you could have had a much better cache hit rate, or maybe you're burning through flash, right? Let's say so bigger caches not only use memory, but they also use flash, right? And so now you start looking at the rates of how much flash you're running through, and you're like, oh no, well, that looks like we're like writing over flash a lot. Let me go back and maybe tune my policy or do something about it, right? And then that has an effect on your cache hit rate, right? So if you're maybe saving fewer items, you have lower cache hit rate. So, and then maybe different engineers are working the two problems, right? So you have this issue where one team is working to improve the cache hit rate, and the other team is trying to improve the rate of burnout of flash, right? And sort of you have people who are adjusting different parts of the system, which indirectly impact the other team without sort of realizing that explicit dependency. I mean, this is a really simple example, and most people would probably figure out that, like, okay, if we're changing this, we're going to impact the cache hit rate. But this should give you a flavor of the types of trade-offs. Now, if you have a single policy controlling the two, then you can set recall on your classifier and sort of make the trade-off very explicit. Okay, I'll get this much cache hit rate at this burnout rate, right? And sort of then you can say, okay, well, this is the classifier I have, and it looks like I can't have both, right? I can't have really high cache hit rate with the current policy and low burn rate. So then what you look at is, okay, maybe we can add additional features and sort of improve both at the same time. Does that make sense? So sort of using adaptive policy tools like Spiral allows you to make those trade-offs explicit and then sort of see them all in one place.
And so you started talking about starting with these policies and then looking at optimization metrics and performance and features and feature engineering, that kind of thing. Can you talk a little bit about the data science element of this or the modeling element of this? And specifically, is that abstracted away from presumably it's abstracted away to some extent from the engineers that are using Spiral, or are they involved in developing statistical models for the specific policies that they want to implement?
So that's a great question, in the sense that this is something we're still trying to figure out kind of the best way to do. So initially, when we started building Spiral, our view was that we have a lot of domain expertise, meaning that if people who are building caches and have building caches for many years decide to use adaptive policy, they actually already have all the domain expertise we need, right? So in some respect, they already know what matters or what doesn't. In other words, if I have written a heuristic manually by hand that checks file sizes and file types and compression types as something that's important to my policy, that is my feature set, right? And sort of I already have experience and I already know what features matter. And that's partially what enables us to do what we do, because the methods, as I said, we use are online methods, and sort of they're meant to be high performance, right? Because a cache is making lots and lots of decisions per second, and you can't really have very heavy models make those decisions. And so currently we partner with teams and help them do the data science. But moving forward, we're trying to template those solutions, and sort of every team can could do their own data science fairly easily with the tools that we built for them, and then they would know how well their system would perform if they were to plug Spiral in. Does that make sense? So in other words, we're transitioning from doing a lot of the data science ourselves and sort of jointly with the team with a sort of high touch environment into more of a self-service environment where teams have an easy way to sort of plug in their data and get the insights and make a decision how to use that data. And this is sort of done through education, through documentation, and through potentially shifting some of the work we do to data scientists on those teams or affiliated data scientists. So that's our path forward to sort of to scaling this, right? Because we're not a very large team. We don't have hundreds of people working on this, right? So it's in order to have impact at Facebook scale, it's if we just were to meet with every potential customer, we would run out of hours in the day.
Sure. Can you talk through the data science process as it exists today, and in particular, elements of the modeling that are unique to the way you've formulated this problem and system?
Sure. So the most difficult, so data science, I guess, in this case, ends up being the part where we are formally defining the problem, right? So effectively, what we do is structured learning, right? So it's really you need features and you need labels, and part of the process to work with teams to figure out what are the features, which is something they usually know, and then what are the labels. And this is something I referred to earlier, which is people don't necessarily agree on what the labels should be and which labels are right. And that's sort of when we bring up some sort of contradictions in the objectives they're trying to achieve. So a lot of it is just talking through the problem and taking a domain-specific problem, sort of a systems problem, and bring it into machine learning terms, and to sort of figure out what is our data set, what are the right answers, what are the right labels. One of the big requirements of Spiral is ability to generate the labels automatically, right? Because in order for a system to stay adaptive, you need to be able to continuously feed back the new labels, right? To continue to adapt to the environment, you need to fit in the new data set, the fresh, correct answers. So a lot of it is, number one, figuring out if that can be done. And if it can't be done, then the Spiral is not the right system for a particular use case. And if it can be done, then figuring out what are those labels, taking them, and then just applying the basic machine learning methods to see if we can achieve desired accuracy, desired quality.
And are there specific methods or techniques that are used particular to the online learning aspect of this?
So one of the very old and very kind of battle-tested methods is something we also use. It's called multinomial naive Bayes. It comes from a family of naive Bayes methods, and it's sort of very simple. It effectively is counting. So if you have let's say one place where this is also used is spam detection, right? So that's actually what made spam detection practical on desktop. When you get an email and it has words like Viagra and something else. Okay, that's spam, right? Because your other email, your good email, probably doesn't have words like Viagra in it, right? That's probably not something you converse about. So that if you count the number of times Viagra occurs in your email, it's very low in good email. And if you count the number of times Viagra occurs in bad email, that's very high. So that's effectively what multinomial naive Bayes and generally naive Bayes methods do. And the big benefit of those methods is that they're incredibly fast, right? Because you're literally just doing counting. There is no gradient descent. There's none of that needs to be done. And as soon as you updated your counters, your model has updated and you're now ready to make predictions with higher certainty or in a larger data set.
You say as soon as you've updated your counters, what do those counters represent? Are those counters features from the input data, or are they kind of internal state that's keeping track of thresholds or things like that?
It's the internal state that keeps track of thresholds. So it's literally like one counter is sort of the prior counter or empirical prior, which is how many good emails have you gotten versus bad emails, right? So if you just count that, and if 99% of your emails are good, and if you ask me to predict that for a new email, is that likely to be good or bad? Based on that single counter, I'll say, well, it's most likely good, because really most of the emails you get are good without even looking at the content, right? And then on top of that, I can look at word occurrences in that email and which words occur in that. And if that email says, hello, Sam, and it says sort of, how are you? Let's get together this weekend. That's one set of words that are being hit, right? And like weekend and hello and everything else, those are all those counts are usually high for good emails. And then if it says, pills, Viagra, something else, those counts are very low in your regular email, right? So does that make sense?
You're basically conditionals in your feature space.
That's exactly right. So you're keeping kind of class conditional probabilities. You're keeping those scores, and you're applying them to as soon as you updated the counters, you have new conditional probabilities, and you could use them to classify the next item.
We've talked about the caching example multiple times. You've mentioned spam a couple of times. Is this used for content filtering types of applications at Facebook, or is that more an example?
That's definitely an example. Just anytime you say multi-node only base, like if you go to onto Wikipedia, they'll literally give you a spam as an example of how this method works.
Are there other areas beyond the cache example that this is being used at?
Yeah, so one other area, this literally can be used in any area where the examples can be generated automatically. Cache is just one of them, in a sense like you know in retrospect which items you should have or should not have cached. Anytime you can retrospectively check a decision, this system applies. And one other specific example is something like retriability. So imagine that many companies run batch jobs, right? So Facebook has a large system that runs batch jobs. And batch jobs often can fail for various reasons, right? Sometimes it could be there is a syntax error that I checked in bad code because I'm an irresponsible developer, right? And there's syntax error in it, and after 4 hours of computing something, it hits my incorrect statement and breaks, right? Literally, the job fails. The results have not been delivered. Or there may be infrastructure failure. Let's say there's network connectivity issues with a particular data center, and the job is trying to get the data, and it fails because it couldn't get the data. Right, and maybe those disappear very quickly. So in the first case, you actually don't want to retry that job, right? But particularly because it could be very expensive to rerun it, right? So you run through a bunch of phases, you run it for hours, spend on hundreds of computers, and then you fail because there is a syntax error. Well,
and you're going to fail again the next time.
Exactly. So I'm going to fail again next time. I can retry it 3 times or 4 times or 5 times. I will still fail, and I will waste resources. On the other hand, if the failure was intermittent, you actually do want to retry, right? And this is it's actually exactly the same setup as with the cache, because retroactively you know what the right answer should have been, right? And certain types of jobs, no matter how many times you retry them, they fail. Other jobs succeed on retries. So learning to classify what to retry and what not to retry is, again, a type of scenario where we use Spiral.
So features here might be job return codes and infrastructure metrics and things like that?
Yeah, features in this example that are literally logs, right? So the return codes plus the log that this job produced. Mm-hmm. So it's kind of just literally the text that was out, that the last say 100 lines of text that were produced, and that's fed into the classifier along with the kind of number of retries that happened. Meaning, okay, this message was produced and we retried it 3 times and nothing good happened, right? We never succeeded. So next time we get the similar message, well, that means we probably shouldn't retry it.
So you've got these logs. I'm imagining a typical log is, has some significant depth to it. It's not kind of abstracted down to a particular, word or error code or something, but it's in there. How are you narrowing in on the specific signal within a big log file?
Well, that's done through the magic of machine learning.
Yeah, I guess in the context of this online learning where you're basically doing counting, right? You've got to tell it what to count, right? You're not. I'm not hearing that you're doing deep learning or something like that, and you're training a model to figure out what to count.
Well, so we are trying to. So there's. It's fundamentally deep learning or any kind of other learning. They're all similar, right? They're all. There is a theorem called no free lunch theorem. You could look it up on Wikipedia, but it's fairly complicated. But in a nutshell, it says that no classifier is superior to another classifier. In other words, if I can, with the right set of transformations on the input data, I can get results that are as good with a simple classifier as I would on raw data with a more sophisticated classifier. Does that make sense?
Sure.
So
Yep.
effectively, if I pre-process the logs using some sort of vectorization, using something else, and then plug them into a very simple classifier, I'll get the results that are almost as good or as good as sort of a sophisticated natural language processing method with recurring neural networks or something
Right.
like that.
Well, that's what I was asking about. You're pre-processing the logs and vectorizing them or creating an embedding or something like that.
That's correct. Exactly.
Okay.
Yes.
Yeah, that's what I was getting at. Okay. Cool. Interesting. And so, one of my initial thoughts, and I alluded to this earlier in the discussion, was, kind of broad implications of this kind of technique in infrastructure management. For example, Google has kind of famously talked about some of their results in applying machine learning to managing, HVAC systems within the data center. It seems like this kind of approach could have similar applicability, correct?
Yes, and that's what we're trying to do as well. I mean, if you work at a large company, sort of a company that with as much infrastructure as Facebook or Google, at some point you want to take people out of the loop, right? And that's exactly what we're doing with our methods. We're trying to make sure people aren't doing kind of routine maintenance or mundane work and are actually focused on creative tasks by automating the routine work and sort of maintenance work.
And so have you done anything to try to apply this to kind of management of physical infrastructure?
Our team in particular hasn't, but I don't know if other teams have. There's many other teams that are doing very interesting things. So we haven't, but I can't speak for all of Facebook.
What were some of the main things that your team has learned in building the system and getting it in the hands of some users?
I think the main thing that we've learned is that you do have to change the mindset of people before they're comfortable using our system. Because initially when they start using it, they sort of just see it as magic. It's like, oh, this magical thing just makes decisions. And then it's like, why did it make that decision? And sort of there's a price for adaptivity. There's a price for optimality, right? And in this case, it's maybe somewhat reduced transparency. So if you think about the example I gave earlier, which is a sort of an if-else tree of statements where your policy is encoded, you could look at any decision and you can trace it back through that tree and say, well, that image was not cached because it was just over the file size limit, right? As soon as you start using statistical methods, that observability goes away, right? It's not where it changes. It requires you to think in different terms, right? It requires you to think in terms of larger data set and sort of statistical averages, not if-else statements. So I think that's the biggest challenge for us. It's sort of getting people to let go of control and trusting a machine learning system. And it's very much on us to prove to them that it's actually better than what they had before. We've been lucky in a sense that we've enabled our customers to do things they didn't think were possible. And so they're kind of embraced us and they said, this is great. This really saves me many hours in a day. And now we can do this thing that I didn't think we could. So that helps. But generally, when you start talking to people, they're a little bit skeptical, like, well, is this going to do the right thing? How am I going to debug it? Right. So that's kind of our next challenge in terms of scaling this to sort of literally every engineer at Facebook, and potentially after that, every engineer in the world who wants to benefit from this.
And have you started exploring approaches to creating some degree of observability, explainability, that kind of thing?
Yes, and so that's a kind of an ongoing process. Traditionally, so this is something actually I learned during the time I worked on my dissertation. Methods such as nearest neighbor methods tend to be easier to explain because whenever a person says, "Why was this decision made?" you could provide examples and say, "Well, because this example looks very similar to those two examples which you said were positive. That's why this example is positive."
Mm-hmm.
Does that make sense? You sort of can.
It does.
It's because nearest neighbor family methods, they work by literally through examples. Like here are prototype examples. Now tell me what this new, never seen before example. What is the label for this example? We can literally use that as an interface and say, well, it's because you provided us with this data. And so that's the direction we're kind of thinking about, and sort of those are the methods we want to try to see if we can exploit and sort of run effectively online.
Awesome. Well, Vlad, thanks so much for taking the time to chat with us about this. This is a really interesting project.
Thank you very much. Thank you for having me on the show.
Awesome. Take care.
Bye-bye.
All right, everyone, that's our show for today. For more information on Vlad or any of the topics covered in this show, visit twimlai.com/talk/221. As always, thanks so much for listening, and catch you next time.